Seminar at 4 o'clock. Today is the first occasion of this kind. There is at least one exception. On Thursday, we do the poster session. And maybe you've seen in the adjacent room that there are poster boards. And I believe they are available for your use right away for those who registered with a poster and do present a poster. So put it up like tomorrow. The Tracy, the program officer, told me that on Wednesday the posters will be removed or put in a corner because they have an interview session all day on Wednesday. So it's necessary to put up the poster before that because the room will be unavailable. It's not enough time to do it on Thursday. So that's that. With that out of the way, I look forward to hearing the first research seminar. And this will be different in style from the lectures in the morning, but still, please ask questions.
Thank you.
I don't think the mathematicians should not expect to understand everything in a physics research seminar, and conversely, the physicists should not expect to understand everything in a mathematics research seminar. Morning lectures, in principle, should be such that everybody can follow. At least that's what we are aiming for. A research seminar is whatever it is.
Thank you very much. I hope I am clear enough because I know that, as you said, most of the people here the audience is largely mathematicians. But coming from a physics background, Anderson is a physicist, so Anderson localization and everything to do with it is just physics. And somehow I felt a bit out of place in the morning seminars when it was so very much about mathematics. But then Anderson localization and related phenomena have grown so diverse that it's not just a thing inside physics, it's now has overarching goals and ambitions. So the work that I have done is on positive Hanbury, Brown and Twist on noise cross correlations in superconducting hybrids. When I talk about superconducting hybrids, these are normal metal and superconducting junctions. And especially I will talk about the role of disorder. What role does disorder play in the transport phenomena in such junctions? The part of the work was published in PhysRev B, and part of the work is I'm currently undertaking. So the talk outline would be as follows. I will first introduce noise, and then I will talk about noise and entanglement, how we can detect and generate entangled states in such systems. I will introduce a historical perspective, how it all came across. Then I will introduce normal metal superconductor and normal metal junctions. I will talk about two very important phenomena which occur, which are cross-on-ray reflection and electron co-tunneling. And I will talk about a very important thing which occurs in such devices, that is, one can detect positive noise cross correlations in spite of the fact that we have negative cross conductance. Now, conductance in such system is just the transmittance, the transmission probability. And finally, I will talk of disorder. What role does disorder play in such systems? If you have a normal conductor and you apply a voltage bias, that means you bias, give it an electric field, you will see you generate a current. But if you look closely as a function of time, you will see that the current fluctuates about its mean value. The fluctuations of the current about the mean value are known as noise. And to detect the noise, what I do is I calculate the correlator of the current correlation function, and which I define as the short noise cross correlation. Here the indices Ig refer to two wires, quantum wires I and quantum wire J, and I detect the noise across these quantum wires.
You mean two
So,
terminals?
two terminals. So the first person to, you had a question?
Yeah, is the other term, is it a function of t or t plus t prime, the average?
The average is detected across t and t prime. But I will talk about zero frequency short noise cross correlations, because experimentally it is very difficult to talk about finite frequency. But I will talk about zero frequency noise cross correlations. And this picture is of Rolf Landauer, who has lots of contributions to localization theory and other things. But he was the pioneer who discovered that one can calculate the noise as such and could relate the noise to the transmittance across a normal metal conductor. Now, there are different types of noise. If you have a circuit and you have a temperature and it's in equilibrium, then the first type of noise is the Johnson-Nyquist noise. Johnson-Nyquist noise is just a thermal noise. At zero temperature, it vanishes, but at finite temperature, it exists. There is another type of noise which is known as the short noise, which would be the subject of my talk. And this is present at zero temperature, and it was first detected when Schottky was the first one to make out this experiment in a vacuum tube. He found that when he applied a voltage to the cathode, the electrons don't reach the anode all at once. There is a time lag. This time lag leads to current fluctuations, which are known as the noise, the short noise. The noise power, as I told you earlier, is the cross correlator, current cross correlation, and it just is a function of the average current multiplied with the charge of an electron. And as I told you before, is this a pointer? Oh, sorry. Okay. So you see, this is a cathode and this is anode, and when electrons are emitted independently of each other, then there is no correlation across the two terminals, and I get completely random noise. This random noise is known as Poissonian noise. When I do a quantum mechanical calculation, however, I see that for fermions, there is something called Pauli exclusion principle. No two fermions can occupy the same state at the same time. And because of that restriction, the short noise for quantum electrons is different from the Poissonian value. You see that the Poissonian value is just a product of the charge and the current, which is the transmittance. But here it was first predicted that in a quantum mechanical calculation, the short noise is reduced from its Poissonian value by a factor 1 minus t. T is the transmission probability. One can intuitively understand the formula of the short noise by just talking about an electron approaching a potential barrier. When you apply a voltage bias V to the left side of the barrier, there are two things that can happen. One is the electron can get reflected or it can get transmitted. I take the averages of the incident current, which I normalize to unity, and the average of the transmitted current is T, and the average of the reflected current is just R. Now, if each particle can only be transmitted or reflected, then the average probability of transmission squared is nothing but T plus 0, because it is this state does not exist, and 1 minus T, which is just the transmission probability. Now, when I take the short noise cross correlation, which is just the fluctuations of the transmitted current, the square of that averaged over, then I will get the average squared transmission minus the average of the transmission squared is nothing but T into 1 minus T. In the early 1960s, two very famous astrophysicists, Hanbury, Brown and Twiss, they wanted to measure the diameter of stars. Now, to measure the diameter of stars, what they did was they took two detectors, set them apart by a certain distance, and tried to measure the diameter of the star. It was an analog of the Michelson interferometer. This picture is not their experiment. This is a laboratory-based experiment, but this is something similar. You have two detectors here, and you are trying to measure the diameter of the star. But unknown to them, what they saw was that the rays from the stars, they could detect at the same time. Now, why did they detect the light from the stars at the same time was that the photons are bosons, and if I get a click in one detector, I have almost 100% probability that I will get a click in my other detector, since Pauli exclusion doesn't hold for bosons. So this experiment was first seen with bosons, and they saw that there was positive correlations. An analog of this experiment for electrons took a long time in coming, but for fermions, as I said, because of Pauli exclusion, in a Y junction setup, the correlations across mu2 and mu3, which are reservoirs, would be negative, and these were predicted by these two people and experimentally seen by these two people. So what is my reason for showing this picture? I started with noise. I talked about the Hanbury-Brown and Twist experiment, and now I will show you, and I will ask a question. If I see positive correlations in a fermionic setup, what would that mean? That would mean that electrons are somehow entangled and they behave as bosons. If I can make an experiment which shows positive correlations in a fermionic setup, I will be sure that I have got entangled states. I have generated entangled states and I can detect them. So my aim is to detect entangled states in a electron based interferometer, and then I want to seek and find out what is the role of disorder, since any quantum wire has impurities and defects. How do they change the cross correlations of the current across my terminals, and do they change at all? Do they reduce it, do they enhance it, or do they destroy it? To check out and to see positive noise cross correlations, I tweak my system and I introduce a superconductor. Now, if I have a superconductor in conjunction with a normal metal, then there is some other type of process which takes place, and that is known as Andreev reflection. One is, in a normal metal system, we have seen that if I shoot an electron at an interface barrier, it is reflected as an electron. But if I shoot an electron at a normal metal superconductor junction, what happens? If it is below the superconducting gap, then it would be reflected as a hole. This process of an electron getting reflected as a hole is known as Andreev reflection, because Andreev was the first one to discover this fact. Now, a hole can be thought of, a hole is absence of an electron or a positron. So, a hole can be thought of as the time reverse trajectory of an electron. You can look at this phenomena in this manner: the two electrons approach a normal metal superconductor interface and generate a Cooper pair in the superconductor. Below the gap, there are no quasi particles in the superconductor. There are only Cooper pairs. So, in such a setup, that is in a Y junction which I showed earlier, but tweaked and replaced with a superconductor, people looked at the current across these two terminals and correlated them to find out if they will get positive correlations. That is, a Cooper pair breaking up into two independent wires. So, these two electrons which are in these two independent wires are somehow entangled. If I get positive clicks in the two detectors, then I will determine that my Cooper pair has broken up into two independent wires, and I get a positive correlation, and that would signify entangled states. So, these two guys were the first people who thought of such a Gedanken experiment, and experimentally it has still not yet been possible to detect it, and I will talk about some difficulties why they haven't been able to detect it. But you can see that where epsilon, which is the transmittance of this junction, is a moderate value, we see completely positive correlations, and when it is fully transparent, it goes to negative correlations. So depending upon the transmission probability of the Y junction, I can modulate my noise cross correlation from positive to negative. If I get positive correlations, that would mean I have entangled states. If I have negative correlations, I don't have entangled states. So my main motivation is to build a solid state entangler in analogy with photon based entanglers. After the Hanbury-Brown and Twist experiment, quantum optics was born, and people worked with photonic entanglers, and quantum optics really came into fashion. But for electrons, it has been very difficult to generate and detect entangled states. Now, the way to detect entangled states, as I showed you, was to tweak it to replace one of the normal metal quantum wires with a superconductor, and then inject Cooper paths into two independent quantum wires, and thus detect entanglement. Now, why do positive correlations imply entanglement? Because we see positive correlations in a fermionic system. Because electrons, they should give me only negative correlations. They are fermions, the way Pauli exclusion principle. Now, to analyze further, introduce disorder into my system, I look at two normal metals coupled to a superconductor, and the superconductor is grounded. That means I don't apply any voltage to a superconductor. I only have voltages applied to two normal metals, and I check out about two processes. Now, electron, if I inject into the superconductor, can get transmitted into the other normal metal, and this process is known as electron co-tunneling. It tunnels from a normal metal to a superconductor, and again tunnels out of the superconductor to the other normal metal. There is another type of process which happens, that is, as I was talking to you about Andre reflection. Now, if I have a single quantum wire conjoined to a superconductor, what I can do, I can break the single quantum wire and separate it, and if superconducting correlations are large enough, then an electron which is incident across one interface can be reflected as a whole in the other interface. This is known as cross Andre reflection. To calculate different quantities, what I do is I replace the normal metal superconductor interface with a disordered potential, and here also I replace the superconductor normal interface with a disordered potential. I solve the problem by having plane waves across the three wires. I match the wave functions at the interfaces and take the first derivative, and then I calculate the scattering amplitudes. What is the amplitude for an electron to be transmitted as an electron, or the amplitude for an electron to be transmitted as a whole, and then I plug in my values in the short noise expression. If I average over the disorder phase, what do I get? This is for ferromagnets. I won't talk about that. Let's see. When Z is 0, that is, there is no interface potential, that is, there is no disorder in my system, I get completely positive correlations. That is, I generate entangled states. When I increase disorder, I see that my positive correlations become negative at certain values of the bias voltage. And finally, in the tunneling limit, when I have a large degree of disorder at my interfaces, I get completely negative correlations when I apply a negative bias voltage, and I get completely positive correlations when I apply a positive bias voltage. But this is a picture where I have two disorder potentials across the normal metal superconductor interface on the left and the normal metal superconductor interface on the right. Well, the first thing about I forgot to talk to you about is the cross conductance, which is the difference between an electron getting transmitted as a whole and the electron getting transmitted as an electron. Now, the cross conductance is usually negative. That means the probability of an electron getting transmitted as an electron is much more than the probability of an electron getting transmitted as a whole. But still then, this negative cross conductance does not imply negative cross correlations. Why is that? we interpret it as some type of a double electron and reflection of two electron co-tunneling. That is, two independent electrons approach the normal metal superconductor interface and they get transmitted as a couple across the superconductor, leading to correlations and leading to positive correlations. Now, before I go into role of disorder in much more detail, let me just conclude, or let me just give the conclusion of the first part of my work. I wanted to detect and generate entangled states in an electron-based system. I have two disordered potentials across my novel metal and superconductor junctions, and I see positive cross correlations of the current, which is defined as the noise, which means that I have generated entangled states. Now, two barriers, if I average over it, they don't lead to localization, or they don't lead to anything different from a classical case. For example, if we check out a Fabry-Perot interferometer with two barriers, and I have an electron, I solve it in a plane wave set. Then, if I have two electron, and I just sum the various paths here, I will find that if an electron just gets transmitted across, it's just a product of T1 and T2. If it gets reflected across this barrier and again comes back and again reflected, then I get a phase factor, which is the phase which it accumulates because of scattering inside these two barriers. And when I sum over all these paths, I will find out that the total transmission goes something like this. And when I take the average of this, I will find out that this total transmission of the conductance is no different from the classical conductance of the transmission. Because if I were to ignore these phases here, which the electron accumulates, and just take the product of the transmissions of these individual scatterers, then I can sum this series also, and I get something which is just the product of the individual transmittance, in the denominator the reflectance of these two scatterers. Now, for two scatterers, I see that averaging over disorder doesn't lead to any difference between the total transmission, the classical transmission, and the quantum transmission here. What about if I talk of three barriers? Now, we saw that for the two barrier case, the total transmittance is same as the classical transmittance. Now, the question arises, do all interference effects vanishes if one averages the transmission probability over a sufficiently large energy interval or over multiple barriers? Now, the simplest case to analyze would be the case of three barriers. If I add another scatterer in series with the two barriers, what do I see? The scattering strength of these barriers are just modeled as R1 and T1, where R1 stands for the reflection amplitude, and T1 is the transmission amplitude. L1 is the length of the between the two first barriers, and L2 is the length between the second and the third barrier. Now, to first order, if I calculate, I can have an electron which transmits across one barrier, gets reflected here, and again gets reflected here. To be simple, I calculate the total reflectance, because it is much more simpler to talk about reflections here. Or if the electron transmits here, gets reflected here, or gets transmitted here, and then again gets reflected, this would take a factor of the L1 and the L2 here, which is this term. Similarly, I can talk of third order process, which the reflection takes thrice between the two scatterers. If I sum again all these paths in a Feynman path integral view, then I can talk about the total reflection. The total reflection would be as shown here. I have averaged over the phases. Now, look at this and then look at the classical result. The The classical result is put up here, and the quantum result is here. There are many more terms in the quantum result than in the classical result. What does this mean? This means that quantum mechanically, when I average over disorder, the resistance of my sample increases. The resistance of my sample increases, and this I can see just from 3 barriers. If I take multiple barriers, 4, 5, I can see it. The calculations are much more detailed, but there also you see this enhanced resistance because of quantum mechanical averaging. Now this, in mesoscopic parlance, is known as weak localization. That quantum mechanically, when you average over disorder, you average over the amplitudes. In quantum mechanics, the difference between quantum mechanics and classical mechanics is that in quantum mechanics, you sum over amplitudes, and in classical mechanics, you sum over the probabilities. And for 3 barriers, the minimal calculation, we have seen that when we sum over the amplitudes, the resistance of my sample is more than the classical result. This effect is called coherent backscattering or weak localization, to distinguish it from strong localization or Anderson localization, which is the subject of this conference. Now this weak localization can be destroyed in 2 manners. If I have incoherent scattering or magnetic field, then the phases will be destroyed and I will get the classical result back. So I talked to you in the beginning of detecting entangled states across 2 normal metal quantum wires with 2 junctions at the interfaces. But we saw here that with 3 impurities, I go into some kind of regime which is known as the weak localization regime, where it distinguishes the quantum from the classical. With 2 barriers, I can't distinguish the quantum from the classical. So what happens when I increase the amount of disordered potentials in my system from 2 to 3? We saw that when we talk about just normal metal samples, from 2 to 3 if we go, the resistance of my sample increases. What about the resistance of this sample when we have a normal metal superconductor normal metal system? I attach another Z prime scatterer here, and I apply the same voltage V1 and V2. I see that my non-local conductance, here it is for the 2 barrier result, this for the 3 barrier result. I average over the phases the electron accumulates when it scatters from this area and it scatters across the superconductor. When I do those 2 averages, I find that the non-local conductance is enhanced in the weak localization regime. Now this is in contradistinction to the classical normal metal wires, where we saw that the resistance increases. That means the conductance, which is the inverse of the resistance, decreases quantum mechanically. But here we see that the non-local conductance, that is the conductance measured in this wire, when I don't have a potential V2, V2 is 0, when I just have a potential V1. The non-local conductance across a normal metal superconductor normal metal junction is enhanced because of disorder. What about noise cross correlations? We saw that noise cross correlations are a signature of entangled states. What happens to them? Let's see here. Z prime is 0 is the black one, Z prime is 10, a very large scatterer. In effect, this would mean that all my electrons which scatter from here should get reflected. There shouldn't be any transmission. The first important thing, there is transmission that is enhanced. An extremely remarkable result. This is just because of coherent scattering, which enhances on-drive reflections. And this on-drive reflection, as I talked to you earlier, is the transmission of a Cooper pair across the superconductor. More on-drive reflections here leads to more generation of Cooper pairs in the superconductor, leading to increased non-local conductance. Now, in a very strange situation, we again see that when I increase my disorder potential here, the 3 barrier case, the weak localization regime in the normal metal case, we see there is an increase in noise. That means I generate more entangled pairs with increasing disorder. So disorder in such samples does not inhibit entanglement, but rather it generates entanglement. So to end, I would say that I have probed some interesting physics in the weak localization regime for a normal metal superconductor normal metal junction. And these studies are important because we want to generate entangled states in solid state systems, and this project constitutes the next generation in detecting splitting of Cooper pairs into different leads. So we show that disorder does not inhibit or destroy entanglement, but can give rise to entanglement. Thank you.
So we have a lot of room for questions.
Oh, hi.
So these graphs you showed, they were from numerical calculations?
Yeah, yeah.
Because the experiments were not successful yet.
Experimentally, I forgot to tell you, experimental till now it has not been, but there have been many attempts to detect entangled states in normal metal systems, in these normal metal superconductor normal metal systems. But unfortunately, although they have calculated and measured the non-local conductance, which shows some very distinctive behavior, very similar to what I have shown here, the short noise cross correlations, they haven't yet managed to see positive short noise cross correlations, but they are still on their way. And I think because one of the important things when you go to these quantum batch, this is the problem of electron-based systems compared to photon-based systems. There is so much scattering, so much decoherence that almost kills off all the entanglement. And you have to go to and make very thin wires. In fact, I have written a paper with graphene, where we show that in graphene it would be much more easier to detect such entangled states.
You mentioned something on applying magnetic field to destroy this.
Weak localization, yeah.
And but then they will interfere with your superconductivity property. Should we apply?
No. When I was talking about magnetic field, that was in a normal metal system, where it destroys weak localization completely,
Okay.
or incoherent scattering. Here, I don't apply any magnetic field. When I talk about superconductor, I don't
okay,
apply.
So you do not
Yeah, that would destroy all weak localization, and in fact, that would also destroy superconductivity in some sense.
Okay, so then we call it a day.
Thank you.
The dinner time, everyone knows when dinner is and where? Estonia, I think. Is it? Quarter past six. Oh, there's a wine reception today. Okay. Yeah, at 5:30, that's about an hour. This is because it's the first day of the program. There's a reception here in the institute. See you there.